Welcome to today's paper reading. Today's paper is titled, MaxMI, a Maximal Mutual Information Criterion for Manipulation Concept Discovery. This paper was published on AR14 by Zhou and Yanchao Yang from the University of Hong Kong. The abstract outlines the primary objective of discovering manipulation concepts from unannotated demonstrations, which are identified as key physical states. These discovered concepts are crucial for training manipulation policies and enhancing their generalization capabilities. Unlike current methods that rely on multimodal foundation models and often suffer from accuracy and semantic consistency issues due to limited robot data, the authors introduce an information-theoretic criterion to characterize these physical states. This criterion, known as Maximal Mutual Information (MaxMI), is used to train a concept discovery network, thereby eliminating the need for human semantics and reducing the cost of human labeling. The proposed framework not only accurately identifies states of high physical significance but also leads to concept-guided manipulation policies that demonstrate higher success rates and better generalization across various robotic tasks compared to baseline methods. The effectiveness of this criterion is further supported by the availability of the source code at the provided GitHub link. Recent advancements in foundation models have significantly enhanced robot capabilities in various tasks such as perception, reasoning, and control. However, the accuracy of grounding high-level manipulation concepts to low-level physical states remains limited due to the scarcity of annotated training data. For instance, multimodal foundation models often provide incorrect answers when asked to assess whether a manipulation concept is achieved. This inaccuracy is crucial as it affects the efficiency and safety of robot learning systems that integrate these models. To address this, the authors propose a bottom-up approach where key states are discovered first, reducing the need for extensive human annotation and improving the grounding of concepts to physical states. Figure 1 illustrates the process of grounding manipulation concepts using multimodal foundation models. In Part A, the concept is grounded by measuring the cosine similarity between the image features and the text embedding of the concept using multimodal encoders from CLIP. This method checks if the image aligns with the described concept. In Part B, a multimodal large language model, GPT-4v, is used to directly ask if the presented physical state achieves the manipulation concept. These examples highlight the challenges in accurately grounding concepts due to the scarcity of robotic training data, which is crucial for the models to understand and interpret physical states correctly. In learning from demonstration, LFD, robots are trained for complex tasks through expert demonstrations, which avoids the need for costly self-exploration. This approach includes methods like inverse reinforcement learning, IRL, online reinforcement learning, RL, with demonstrations, and behavior cloning, BC. Foundation models, such as large language models, LLMs, and vision language models, VLMs, are used in embodied planning to convert language instructions and environmental information into control signals. However, these models lack the ability to accurately identify low-level physical states corresponding to high-level concepts. Hierarchical planning decomposes complex tasks into simpler subtasks across various abstraction levels, facilitating policy learning, and leverages techniques like the chain of thought, COT, prompting. The goal is to localize key physical states within demonstration trajectories that represent manipulation concepts. Given a dataset of n pre-collected demonstrations, a neural network is trained to find the temporal indices of these key states. The Maximal Mutual Information (MaxMI) criterion is proposed to enable training without manual annotations. This criterion suggests that key states, which correspond to manipulation concepts, maximize the mutual information with their preceding states. A localization neural network is used to discover these key states by maximizing the MaxMI metric, which involves fusing state information with learnable concept embeddings. Figure 2 illustrates the concept of maximal mutual information, MaxMI, in the context of key states within manipulation tasks. The figure demonstrates that the mutual information between a state variable and its preceding state reaches its maximum when the state variable corresponds to a key state, which is a manipulation concept. This is verified across 4 different manipulation tasks: turning a faucet, inserting a peg, picking a cube, and stacking a cube. The sub-figures in the figure highlight the specific moments when the mutual information peaks, accompanied by images that depict the corresponding key states. This consistent phenomenon suggests that by maximizing the mutual information quantity, one can effectively discover and identify manipulation concepts within the tasks. Figure 3 illustrates the Key State Localization Network, KSLNet, a framework designed for manipulation concept discovery. Each key concept is represented by a learnable embedding, EC, which is appended to all state vectors along a trajectory. These augmented state vectors are then processed by a fully convolutional encoder and a multi-layer perceptron, MLP, to derive the probability, PIC, of each state being the identified key state. This network aims to localize key states by maximizing the mutual information criterion, contributing to the efficiency and accuracy of concept discovery and manipulation tasks. In this section, we evaluate the proposed key state discovery strategy. We begin by setting up our experiments with major baselines including behavior transformer, BET, decision diffuser, DD, decision transformer, DT, and chain of thought predictive control, COTPC. The experiments are conducted on complex multi-step tasks from Monty Skill 2 and Franca Kitchen environments. We train our policies using behavioral cloning with 500 randomly sampled trajectories. Next, we compare the manually annotated concepts with those discovered by our method. Our approach shows flexibility in adjusting the number of key states and exhibits a high degree of similarity with human annotated concepts. Finally, we present quantitative results showing that our method outperforms various baselines in terms of task success rates and demonstrates effective generalization in novel scenarios. Figure 4 presents a comparison between manually annotated key states and those discovered by the proposed pipeline across 4 distinct tasks: pick and place cube, stack cube, turn faucet, and peg insertion side. The figure demonstrates that our method not only identifies key states that align with human semantics, but also promotes more fine-grained manipulation concepts. This capability is shown to effectively benefit concept-guided policy learning. The comparison highlights the method's ability to discover concepts that resonate with human understanding of the manipulation process, enhancing both interpretability and applicability in complex scenarios. Figure 5 illustrates the variation in key states discovered using different terms discussed in Table 5. The pairwise distance term is observed to enforce diversity among the discovered concepts but alone cannot ensure semantic meaningfulness, thereby simply exhibiting a uniform distribution across the trajectory. In contrast, relying exclusively on the MaxMI criterion tends to discover clustered concepts around the state with the highest mutual information value, thus reducing the diversity of the concepts. The full model, however, can discover more meaningful key states while maintaining diversity. Table 1 presents the success rates, SR, of policies trained using discovered concepts and various baselines across multiple tasks. For complex tasks like peg insertion, the success rates for intermediate subtasks such as grasp and align are also reported. The table compares the performance of different methods, highlighting the superior performance of the proposed method in handling complex multi-step tasks and achieving the best performance consistently. This validates the effectiveness of the proposed method in localizing physically meaningful key states and enhancing the generalization of trained manipulation policies in new scenarios. Table 2 presents the success rates of policies trained using our discovered concepts and various baselines across multiple tasks, evaluated with initial configurations unseen during training. For complex tasks like peg insertion, success rates for intermediate subtasks such as grasp and align are also reported. The turn faucet task is evaluated with faucets of novel geometric structures, zero-shot. The table highlights the performance of different methods including DT, COTPC, and our proposed method, showing that our approach consistently achieves higher success rates across various tasks and subtasks, indicating superior generalization capabilities in new scenarios. Table 3 evaluates the performance of concept-guided policies in the Franca Kitchen environment, where a 9DoF Franca robot operates within a virtual kitchen featuring 7 object interaction tasks. The performance is measured by the number of tasks completed out of 100 episodes, with higher numbers indicating better policy performance. The mean column denotes the average number of tasks completed per episode. The results show that policies trained with discovered key concepts can effectively reduce the decision horizon, allowing for more subtasks to be completed within fixed steps in one rollout. Table 4 presents the success rates of various key state selection strategies across different tasks and conditions. The last state strategy shows moderate success rates but struggles with unseen conditions. Our strategy, ours, demonstrates significantly higher success rates across both seen and unseen conditions, particularly in tasks like PNP cube and stack cube. The compile 25 strategy also performs well but is outperformed by our approach in several tasks. This table highlights the effectiveness of our key concept discovery method in improving policy performance. Table 5 presents the success rates of policies trained using key states discovered with different loss terms. The only PD method, which uses pairwise distance regularization, shows success rates of 66.6% for PNP and 67.4% for cube stack. The only MaxMI method, based on the information-theoretic criterion, achieves 73.2% for PNP and 66% for cube stack. The proposed full model, ours, demonstrates significantly higher success rates, with 91% for PNP and 88.6% for cube stack, indicating its effectiveness in discovering more meaningful key states while maintaining diversity. In this study, the authors propose an information-theoretic metric designed to characterize the physical significance of key states in robotic manipulation tasks. This metric is utilized to develop a self-supervised manipulation concept discovery pipeline, which can identify meaningful key states. When these key states are used to guide policy training, they result in higher performance compared to a wide range of baseline methods. The necessity of the proposed terms is validated through an extensive ablation study. However, the study also identifies a limitation. The MaxMI criterion alone may not ensure the diversity of discovered concepts due to its local modeling characteristic. To address this, the authors suggest that future research could extend the metric to a multi-scale concept discovery framework, allowing for the incorporation of global information from trajectories. Thank you for watching.